All right, I just got to find our notes. I just put a copy in here, I think. Yep. Oh, that's the wrong one. All right, so a lot of these preliminary questions that we have up here, we're gonna really just quickly go through, okay? And just it's just conversation starters basically, and we're gonna really just spend a lot of time on the exponential stuff, the newer stuff in this topic. And if we had additional time to do this, like we had a whole week or whatever, yeah, we would I would this would be investigative, a lot more group discussion, this kind of, and we're gonna still do some of that. But a lot of the preliminary stuff here, we're gonna try to get through as fast as we can, okay? All right, so uh, we're going to start talking about here something that doesn't necessarily grow by the same rate or decrease by the same rate at for every new interval, or every new entry of time or whatever it might be. Okay, it's going to grow or decrease at different rates. Okay, at each time. So we can discuss how that happens. And one of the classic examples of how this comes to pass is by looking at the value of a home. Everybody has a home. If you've purchased a home before, you know that your value of your home usually increases over time. Okay, depending on how kind of improvements you make over it and stuff like that. All right. At one point in time, they said that, and inflation helps with that too. I mean, inflation can sometimes increase the value of a home also and stuff like that also. So, all right. So let's assume that in 1960, Tony's grandparents, not Tony, but Tony's grandparents bought a house for $10,000. Okay. Now, the rule of thumb is that for every 10 years that pass, or a decade that passed, that should double every year. Okay. So, just out loud, what would be the value of the house 10 years after 1960? 20,000. What would it be again in 1980? Okay, let's write those down here real fast. Okay. Okay. So what's happening here? What would it be in 1990? 80,000. Okay. So what's the difference between 1960 and 1970? Well, 20,000 minus 10,000 is 10,000, right? Okay. And what's the ratio? 20,000 over 10,000 reduces to what ratio, kids? 2 over 1. Am I going too fast? Okay, this is just some basic math at the beginning, I think, okay? So we're going to really quickly here, we're going to fill in this table, okay? So decades since 1960, 1, 2, 3, 4, 5. Okay? The house, 10,000, 20,000. I want to make it nicer to read. 40,000, 80,000, 160,000, and 320,000, right? Everybody good with that? What's the difference between the consecutive decades? Well, check this out. 20 minus 10 we just did. 10,000, right? Then 40 minus 20. 80 minus 40. Right? 160 minus 80. And then finally, just another pattern, correct? So the next one says ratio of values of consecutive decades. So that's comparing 20 over 10. What's that become? Right, 10,000, right? Or 2. It becomes 2, correct? 40 over 20 becomes 2, right? 80 over 40 becomes 2. 160 over 8 becomes 2. Yep, and really it's not, I'm doing this wrong. I shouldn't be doing these numbers here. I should do it with these numbers here. 20 over 10, 40 over 20, 80 over 40, 160 over 80, and 320 over 160, right? But in each case, the value was what? What's the ratio? 2 to 1. That's interesting, right? Okay. Does that make sense that it should be that because it said it doubles every 10 years? Yeah. Okay. But is the rate of change constant per decade? Is the increase the same amount each decade? No. Okay. No, it is not. Okay. So we just did number 5 verbally. Is everybody okay with that? Okay. Let's go ahead and plot these points on this graph. All right. So I'll put the points up here where you can see them. And we'll get our scales here finished up here too. Okay. I'll bring those up here in just a second. Let's get our graph here ready to go here. 1, 2, 3, 4, 5, 7, 8, 9. This goes by 40s. So this is 40, 80. Excuse me. 120, right? 160, 200, 240. It's a really bad 8, 280, 320, 360. Are we okay with that? You guys remember the values? So at 1960, that's 0. Okay. What was the value? 10,000, right? So here's how I'm going to get this on the right. Halfway would be 20. There's halfway. Half of half would be 10. So there's where the 10,000 goes. Okay. After 1 decade, 20,000. After 2 decades, 40,000. Am I okay so far, everybody? What would it be for 3 decades, class? What was the value of the house? 80,000, right? 4 decades? 60. And then finally 5 decades? 320. Okay. My question here is number 7, okay, that you can't see up there, but I'm going to shrink this down a little bit so we can see it, all right? Should you have expected a straight line for this graph? Okay. Why not? Talk about it with your group mates for 30 seconds.
Because it isn't increasing.
Okay, and let's take it. Mason?
So it isn't like a steady increase, so it wouldn't be a straight line.
The rate of change is not constant, right? Well, but there was something constant. That's not the same thing.
It's the pattern.
It doubled each 10 years, right? The amount doubled each 10 years. Why doesn't that equate to a constant rate of change? Sadie?
Because it doubled itself. So like,
Mm-hmm.
so like 28 goes to 40 and then like so it doubled itself.
Right. Okay, exactly. So it doubled itself, so that was consistent, but it doesn't necessarily mean that the rate of change between decades is going to be the same amount, because you're doubling it. Okay? Are we all okay with what this reasoning is? This is the reasoning we're going to talk about here and how we develop exponential functions. This is a example of an exponential function. Okay? Notice the graph is not a straight line. Okay? And theoretically, if you really wanted to, you could connect these points together. Okay? It'd be a little bit tricky, but you could do it. Something like so. What would be the next value after 320? 640. Okay? Everybody see how that works? Yeah. Okay? Very good. Very good. All right. So, are we okay with how this is all coming into play here? All right? So, I'm just going to put down here for number 7, the rate of change is not constant. Okay? Are we good with that? Show me a thumb. Are we okay with that, everybody? Good. Good. Okay. Let's keep going here now. All right. We actually kind of did that next one, number 8. We kind of did it already because I said what would be the next value of the house, right? After 320,000, wouldn't that be 2020 for number 8? So you guys agree that that would be the right value to put there for a prediction or not? Show me on your thumb. Agree or disagree? 640,000. What do you think? Would that be the right value? So the previous decade was 320. Okay. The next one would be, that was 2010. Okay. So the next one would be 2020. All right. So the prediction is that, or what our speculation is that it should be $640,000. Agree or disagree? Okay. All right. Okay. How we do that? We just doubled the amount, right? I'm going to put this in parentheses again. Okay. All right. So we're going to give you guys a chance now to look at problem number 9. Okay. And I'm going to get a prediction from each group, what they think the amount would be of the house for 2005. Okay? You know what it is in 2010. You know what it is in 2000. I'll put those values here to the side. I believe 2010 was 320,000, and 2000 was 160,000. Okay? So what would the value of the house be in 2005? All right? Turn and talk to your group mates. I want to get 4 different predictions. Okay? Go.
Yeah, if we have
You guys have numbers? Okay. Anyone want to venture a guess? Okay, let's start. We're going across the room here. Red group, what did you guys decide? 240,000. Blue? Green? Yellow? Me? About 226,000. I see a lot of head shakes. Does it make sense? I heard somebody say, does it make sense? Thoughts? Emily?
We estimated that it would be a constant amount between 2005 2010, but because our line isn't constant to begin with, it should be a constant rate, meaning that you're correct.
Did you just assume a linear relationship when you made your prediction?
Yeah.
So what happened? Emily thinks that's what happened. You guys agree with what you say? That you assumed that the rate would increase by the same amount between 2000 and 2010, and you just take the halfway point there. Okay, you really just took the average number between 160 and 320, right? Basically. thinking that the growth between that decade would be the same each year. Is that actually what's happening? In reality, if I click looking at the graph, is that what's actually happening? Fortunately, it's not. Okay? More growth would take place at the end of the decade versus before the beginning parts of the decade, right? So you get more growth after 2005 to get to $320,000 by 2010 than you would between 2000 and 2005, right? I'm going to show you how I got that number here in just a few minutes. Okay? I kind of cheated a little bit on this one, all right? I knew what the answer was supposed to be. I kind of cheated a little bit on this one, manipulated it just a little bit. More so than I'm used to. Okay? Yes, I know. I manipulate things all the time, right? But this one I kind of took a little liberty. That's the things that you didn't have to review information. Okay? So let's talk about what an exponential function looks like, okay? In its most general form, an exponential function has this form. F of x equals a times b to the x. Okay? So this time, x is our exponent. Okay? X is our exponent. All right? B, okay? B is our constant ratio. What was that value regarding this scenario? What was the constant ratio between decades each time? Raise your hand. Tony? 2/1. So that would be B. Okay? So exponential functions, they don't have a constant rate of change. They have a constant ratio. Okay? So the ratio of values between time intervals is the same. Okay? But not the actual rate. Does that make sense? Okay? That's the difference between a linear function versus an exponential function. All right? Exponential functions have a constant ratio. Linear functions have a constant rate of change. You guys see the differences here? It's a little bit different, okay? So, I know it down here at the bottom of my screen, down here on the page, it tells you the function for this relationship, but let's try to figure this out. A, okay, is the initial value. So let's highlight some things here, okay? Let's just get some stuff highlighted on here to help us out. So A, whoops, use my highlighter. That would help a little bit. A is the initial value, right there, okay? And B is the constant ratio, okay? And then you know you have X up there. X is the domain value, okay? So in this case, X would be the decade. Are we okay with that? All right. Now, these restrictions right here are very, very important, all right? Because we'll talk about these a little bit more another time. But these restrictions are important, otherwise you don't have an exponential function. A cannot be 0, B must be greater than 0, and B cannot equal 1. Okay? If those restrictions are not met, we do not have an exponential function. All right, we'll talk about that later on in our discussion. Okay? All right, so what was the initial value of Tony's house? 10,000. So I can write a function, f of x equals 10,000, right? That's the initial value. What was the constant ratio? Times 2. And for whatever decade I want to find it, I let x equal the decade. That's the function for the situation. Does that make sense? Okay? For example, let's try it out. Let's pretend I want to figure out the value of the house for 2 decades after 1960, okay? So, with me all together, class, x would be what value? 2. Okay, what is 2 squared? 4. What is 4 times 10,000? 40,000. You see how it works out? Are we okay with this? Okay, good. Okay, that's really all it comes down to. All right? All right, so I give you that value, okay, in number 11, or above number 11. So number 10, I'll put constant factor of 2 again there. Then look at number 11, okay? We talked about this just a little bit ago, right? H of t would be what? Value of the value of the house. Okay. T is the decade since 1960, right? Decades. We okay? All right. So here's the deal. Okay. Number 12. What's 10,000? What is 2? I just told you this stuff, right? 10,000 is what value? It's your initial value, right? Okay. Okay. B is 2. That is the constant ratio. Okay. I know it's a lot of quick writing and listening, okay? But we're going to get to some other stuff here soon. All right. If I wanted to calculate the amount of the value of the house in 2020, okay, how would I do that? What would be the value of T, okay? Of H of T equals 10,000 times 2 to the T, right? T would have to equal what value for the year 2020? Raise your hand if you think you know what it is. Remember, T is the decades since 1960, okay? So what would be the decade number I need here to get 2020? Okay, Merrick? All those in favor of 6. 1960 is 0. 1970, 1980, 90, 2000, 2010, 2020. It would be 6. Are we okay with that? All right, so how does this work? H of T equals 10,000 times 2 to the 6th. 2 to the 6th is what? No. That's a common misconception. Okay? It's not 2 times 6. It's 2 times itself 6 times. Okay? Just like on some people's assessments in both classes. 5 to the 3rd is not 15. 5 to the 3rd is 5 times 5 times 5. Okay? It is 64. Okay? Don't fall for that trap. That's a trap. Okay? So I have 10,000 times 64, and I get $60,000. No, I'm sorry. That's not right. How about $640,000? There we go. I was a digit short. Okay. Are we okay with this so far? Now, work together in your groups and complete problem 14. Okay? I want you guys to figure out, okay? I want you guys to figure out the exact value of the house in 2005. Okay? If you're having trouble, I would start figuring out what T is first. What is T? Well, that's something you can discuss with your group mates, okay, Mason? I'm not saying that's, I'm saying at this point, anything is on the table, okay? Anything is possible. Go ahead and converse it back. That's fine. You can work on it together. No problem with that. Okay? I suggest you figure out what your T value is first, and then you can plug it into your equation. And calculators are absolutely allowed. Okay, so you can use your calculators to figure this stuff out. Okay? You might have seen it online earlier. Are you guys ready to turn and talk? Let's go, okay? Get a couple answers here for me out, and we can talk about it. You guys figure out what your decade was and what your t-value was?
Yeah, that's right.
How do you do decimals in exponents?
You should use a calculator.
Same way. Just use a calculator with it.
So if you do 4, if you take 4, like 2 to the power of 4, and then you divide it by 2.
You need the more sophisticated calculator there, Mason. Yes.
The scientific one?
Yep. And your X to the Y button, where's that at? Oh, I saw it. Right there. Okay, so you want to do like 10,000 to the 4.5, do 10,000, then hit the button, do 4.5 and then equal. Okay. Yeah. Right, do 2, X to the Y, 4.5, equal times 10,000. Bingo. Round to dollars and cents. Round to dollars and cents. Okay? You know what that means? How many places for dollars and cents? 2. You got it. Okay? Round it to dollars and cents. All right. What are you guys doing to figure out the value for t that you need? I hear a 4.5 in the works here. Is that what everybody else agrees with? 4.5. Okay? 2005 is halfway between 2000 and 2010, right? 2000 was decade 4. 2010 was decade 5. So then it makes sense that that would be 4. Are we good with that now? Excellent. Okay. Now, this then becomes a calculator problem. Follow the order of operations. All right. You need to locate on your calculator the button that looks like an x to a y exponent. That's all, for a lot of the calculators that I see. Okay. If you don't have that button on there, then you're gonna have to look for one that has like x to a blank square on it. Okay. Or something to that extent. Desmos might be something similar to that. I forget at the moment what Desmos is. Okay. Yeah. Okay. Exactly. All right. So it's going to be 10,000. Okay. 10,000 times 2 to the 4.5 power. Okay. 10,000 times 2 to the 4.5 power. So you're going to do 2 to the 4.5 power first. Get a number. Okay. Take that number, multiply by 10,000. Are we good? That's all we have to do. Okay. You're trying to plug these numbers in. Please use your calculators. How close was I? Pretty close. I've had experience too. Okay. I've been around the block a couple of times. But isn't that interesting? That there's about what? What was it? It was 226, right? So in 2000 it was 160, right? 160. So what? That's about I don't know. That 86,000. Okay. So what is the exact value here? 226,000. I'm looking over you, Tony. Just a minute, okay? $274.17. Okay. Good. All right. Excellent. We're going to skip 15 for a minute, but remind me, we need to come back and discuss that. Okay, that's important stuff. I just want to start talking about the next section here for a few minutes. Excuse me. And maybe get through a little bit of that preliminary work. All right, so then when we come back on Friday, we can dive right into the exponential stuff. Okay? And then Friday, we'll have a little bit more interactivity and stuff like that. All right, so this was an example of exponential growth. Over time, the numbers got bigger, correct? All right, so here's an example now that involves something different. Okay? Have you guys in chemistry at all talked about what a half-life is of an element? Have you heard the term half-life before? Okay, so here's the quick answer for that. So you have an element, you have a certain amount of it. Okay, radioactive elements have a half-life. Okay, radon is a big example of a radioactive element. You guys might have radar sensors in your basements. Okay, that's why, because they want to make sure that the amount of radon in the basement is not at a radioactive level. Okay, it's like that liquid in that thing that you have to be between certain marks or whatever, so that everything is on the up and up. Okay, so here's the deal. Every radioactive element has a half-life. That's the amount of days it takes for the half of the previous value remaining of the element. Okay? So for an example, I have an element and the half-life was 2 days. Okay? And I start out with 20 units of this element. Then in 2 days I should have 10. Okay? And in another 2 days I should have 5. And in another 2 days I should have 2.5. Okay? Everybody see how that works? Yeah. All right? Exactly. So, we're going to do this here with this idea. Okay? So, radon has a half-life of approximately 4 days. Okay? In Tony's grandparents, sorry, Tony. Okay? In Tony's grandparents' house, they figured out they had a radon concentration of 400 units. Okay, I'm just going to, that's called picocuries per liter. We're just going to say units. All right? Make it easy on ourselves. Okay, so if you start out with 400 units of radon, after 4 days, if that's the half-life, raise your hand. How much should be there? Raise your hand. Blake?
Oh, I didn't raise my hand.
Oh, I thought you did. I'm sorry. Can you answer me real quick anyway? The half-life is 4 days, and I'm asking how much would be in the house after 4 days if you start with 400.
Start out with 400.
Uh-huh. And the half-life is 4 days for radon. How much radon would be left after 4 days? Half of it,
Yeah.
which is
200.
exactly right. Okay, everybody okay with that? After another 4 days, how much would be left, class? 100. After another 4 days, how much would be left? After another 4 days. Do you see how this is working out? What's happening on this example? They're getting smaller, right? They're getting a lot smaller. All right, so, okay. What's the amount left over? 200. The difference in the amount, 400 minus 200 equals 200. Okay. What's the ratio from day 4 to day 0? Okay. We'll worry about that in a minute. Let's go on this table. Okay. Days after radon source was eliminated. Okay. So, 1 half-life. That would be 4 days, correct? Another half-life would be 8. Another half-life would be 12. 400 goes to 200 goes to 100 goes to 50. Okay. What's the differences? 200, 100, 50, right? What's the ratio? 200 over 400. What's that become? 1/2. How about 100 over 200? 1/2, right? How about 50 over 100? 1/2. What's happening here? We're decreasing, right? Okay. We're going to stop it here so we can start with the graph first thing on Friday, okay? For our homework for this section, there's just one assignment. It's chopped into 3 different parts, though, okay? Try to work some in part 1 for tomorrow. I'm not going to submit anything yet. Just work some in part 1 so far you can get along, okay? And we'll take some questions on that maybe on Friday, too. Thanks, guys.